So what I'm going to do now in this second half of my presentation is I'm going to try to flesh out the ideas that I pointed out in a little bit more concrete details. In particular, there's a couple of things I want to warn you. First, once you have come up with the right space representation, actually, in some sense, you will not even need to use neural networks. You could use any other type of approximation, but it just happens to be the case that neural networks are going to be a little bit more convenient. But I just want to warn you that, at the end of the day, really the very key thing over here is the permutation invariance. It's not the neural network itself. And now, also, I want to show you or motivate the application that I will use in the rest of the talk, which is going to be the problem with all these type of things. So, I have been writing papers on computation since I was in graduate school, many more years that I care to remember. And this is a catch-22. Okay, so I don't know if you have read the novel, but the novel, basically the idea is you can request, you're a pilot, you're a bomber pilot, and you can request to be taken out from front line of combat because you think it's too dangerous and you have a nervous breakdown. But if you realize that that's the situation, it means that you have not really had a nervous breakdown yet. So you cannot be taken out. That's why it's called a catch-22. And this is the situation with every computational paper. I can come up with a very complex model where really taking advantage of all these new computational methods makes a huge difference. And then everyone will be, oh, but I want to see the simple application where everything is very transparent. Or I can have a very simple application, and then the very same person that in the counterfactual will have asked for the simple application will ask for the complex application. And believe me, I'm not going to name names, but that happened to me once because I had a paper with a simple and a complex application, and I presented the simple application in one seminar, and that person asked me about the complex application, and then that person was in the MBR Summer Institute 6 months later and didn't remember the paper, and I presented the complex application to make him happy, and that person raised their hand. I say, oh, obviously you should have presented the simple application. Anyway, it's a nice lad, but nonetheless.
What was your response after the second presentation?
I was an assistant professor, so I smiled.
Okay.
Now that I am a full professor, I may have been a little bit more forceful on my answer. But being an assistant professor, I smile, I know that, and I say, oh, I have the more simpler application. Let me show it to you. Anyway, what can I do? Now, so what I'm going to do is I'm going to show you a little bit of a simple application, but that I like a lot. And hopefully you will be able to understand how it goes. And this is by Lucas and Prescott, their famous model of investment in 1971. This paper is very interesting for two things. This is when both Bob and Ed were trying to figure it out, dynamic programming and recursive competitive equilibria, and they were struggling with it. And it was one of the first models of really where you have like many different firms doing investment, etc. And beyond its historical value, it has 4 great points going for it. First of all, if you take Loomschmidt and Sargent, the standard macro textbook is the very first model that they use to introduce recursive competitive equilibrium. Okay? So if you go in the latest edition from pages 226 to 228, that's actually the model they use. So you can go to Loomschmidt-Sargent and check immediately what we have. The second thing is a model that is going to fit on one slide. So I don't need to spend 25 minutes going over the details of the model. Third, under one particular parametrization, the model has a known LQ linear quadratic solution, which means I can solve the model using my symmetry system and neural network. I can get a solution and I can benchmark it against the exact solution. And I can convince you they are on top of each other to like as many zeros as you want. But then by changing but just one parameter, the model becomes as highly nonlinear as I want. You cannot solve it in any other way. I will be able to solve it, but using Euler residuals, try to convince you that we can do it with very high accuracy. So it's a very convenient model because it's just about one parameter, either LQ or not LQ. Okay. So I'm going to introduce the big X, little x dynamic programming problem. You may have seen this as big K, okay. It's at the end of the day the same idea. So I have an agent, and this agent has a value function that depends on an individual state, lowercase x, and an aggregate state, capital X. The trick of little x, big X, or the other way around, is that the agent is not going to take account when it makes its decisions of how it's changing the aggregate state of the economy. Okay? Now, of course, this is not absolutely true. If I save a little bit more, the total amount of capital in the US economy is going to change. But the idea is that even if I'm not literally a measure zero, is sufficiently small that it's going to be an effect of 0.00001, I may as well forget about it. Okay? So I'm going to take account that my actions determine my states, but I'm going to take aggregate states as given, even if my actions affect aggregate states. Okay? And this is a very good approximation as soon as you have 5 or 6 agents in the economy, and in a continuum, then the approximation will be exact. So my value function is going to be equal to the Bellman operator. Max of U, where U is going to be my policy function, my decision rule. And I'm going to have a return function. I'm going to write this at this moment at a sufficiently general way so you can think about many dynamic programming problems. And my return function is going to depend on my own states, the aggregate states, and my decision rule. Okay, so this is as a standard as you can imagine. And then I have a continuation value, which is my discount factor beta, the conditional expectation of my value function tomorrow. And the way I'm going to build my conditional expectation is taking account that my states tomorrow depends on my state today and my choice, and individual shock, and an aggregate shock. Yeah, and again, I'm trying to do this as general as possible. Maybe there is no individual shocks, maybe there are not aggregate shocks. I'm just trying to set up this in a sufficiently general way. And then we are going to have something similar for the aggregate state, where the evolution of the aggregate state is going to be a function of the state today, the aggregate shock, and a vector with all the individual shocks. And the point here to remember, again, as I was saying before, is that I understand how the aggregate state evolves over time, because I know, imagine this is me and you are the rest of the economy. I understand how all of you are behaving, because all of you are following your optimal policy rule. Okay? The only thing I'm doing is I'm shutting down the strategic aspect of me, taking account that by doing something, I'm changing what you're doing. I can come back to that later because there is a straightforward extension of this for a strategic interaction, which I think would be a very nice application in the case of industry dynamic models with a few number of agents. Actually, I try to convince a student to, figure out how to do this for an Ericsson package model, and he promised I will come back to your office about 6 months ago. Well, anyway, I will probably ditch him and find someone else. Anyway. So let me introduce some ideas. A permutation matrix is going to be a square matrix with a single one per row and zeros everywhere else. And these permutation matrices are called in that way because by pre-multiplying a conformable matrix A, they permute the rows. Okay? So the idea is going to be the following. Remember my example before, I'm General Motors, you are Toyota, you are Mercedes. I'm going to...
You really insist on that.
Well, no, but that's the bad thing now, because now I'm going to permute them. So the permutation matrix swaps. Okay? So I'm going to have those permutation matrices. And I'm going to let Sn be the set of all the possible permutation matrices that we have over n agents. So if I have a model with 50 agents, I'm going to have 50 factorial possible permutation matrices. So basically the idea is the permutation matrix applied to this classroom will be all possible combinations. Imagine that this is a model, I'm writing a model about this classroom, and the only thing that matters for our optimal decision is where you are located, where you are seated. So the permutation matrix basically is all the possible recombinations of everyone in this room with respect to their seats. And if there is, I don't know, how many people is in this room now, like 60? There is 60 factorial possible permutation matrices. So for instance, in a model with 2 agents, I have the identity matrix, which is basically I let everyone seated where they are now, and I have flipping around. Now, if you know a little bit about group theory, you will know that S sub n is the symmetric group. Okay? I don't want to say a lot about group theory, except 2 things. One, a lot of the heavy lifting in the proofs rely on the very deep properties of the symmetric group. I invite you to go to Wikipedia. Wikipedia in math is actually surprisingly good, not like in economics, which is pretty crappy. And just check the Wikipedia entry for symmetric group. And you will spend like 3 hours because it's so fascinating. And if not, get yourself a good book, one of those Springer Verlag yellow books on the symmetric group, and you will find how it's so fascinating and how you can make so many groups. Okay, so why is it important about group theory? Okay, let's think about people like Galois when he starts developing the group theory right before he decides to get himself killed in a stupid way. And you know that Galois got killed like in a stupid duel. Yeah. Okay, so I mean, how that can be like Hamilton. Anyway, basically the idea is I'm going to study the properties of an object of interest. In the case of Galois, it was some type of PDEs of partial differential equations, not by studying the partial differential equation itself, but by studying the type of operations I can apply to that partial differential equation. And that's what I'm going to do here. I'm not going to look at the solutions per se of the dynamic programming. I'm going to look at the type of permutations I can do of the solutions of the dynamic programming. And you will see in a second how this is going to go. But more generally, the word symmetric is already highlighting that geometric interpretation I was telling you before about how what really matters is looking for the right geometrical space. Okay. So let me introduce a definition. A big X, little x dynamic programming problem is a perturbation invariance dynamic programming problem if for every possible combination of states, individual states and aggregate states, if I permute the aggregate state distribution, my optimal choice is the same. So this is very straightforward. Again, imagine that this is a model of investment in the car industry, and General Motors, and all of you guys are all the other car companies in the world. The only thing that I care about is that there are going to be 3 companies with high productivity, 4 companies with middle productivity, and 8 companies with low productivity. The labels attached to those companies are irrelevant. Basically, what I'm trying to say is the following. The top row of what I'm going to write down is my own state. So I'm high productivity, and then the rest of the economy, the rest of the industry is high, low, high, high, high. My statement is my investment decision in this wall will be the same that my investment decision in this wall, and it will be the same that my investment decision in this wall. because the only thing that I do is I care about my own state and the distribution of all the other states. Exactly who is low is either firm 2, firm 3, or firm 4. I do not care. Okay? And again, that's in the Packers-Erickson tradition. Yes.
The first column has 5.
It's 5 o'clock.
But can you talk about this little wrinkle that one of them is me?
Yes.
So I don't want to permute myself, right?
Yes.
I don't want to suddenly
Yes.
make myself a low productivity.
Yes, but remember that this is a wall where in the big X, okay, so I was trying not to do this too strictly. One kind of counting yourself twice. Okay, so what I'm doing is I'm permuting this. Okay, so there will be like another set of permutations over here. And the fact that now myself, when I'm thinking of myself as part of the aggregate, the fact that I just changed my states with him doesn't matter. Because my individual, remember, the way I'm writing the theorem is my X is still my X. Okay? And that's the part where this paper deserves the extension to fully take account of the strategic component. Where I will really know that by changing myself, I'm affecting everyone's component. Now, the important point is, think about a very simple prisoner's dilemma. In the prisoner's dilemma, the best response function is symmetric. And I think that in general, in game theory, as far as I can remember, most best response functions are symmetric. Because you can always index them by, if there are differences in payoffs, you can always index that as additional values. So I think that extension to strategic interaction over here is relatively easy. Okay, but that's the point. I'm going to say my dynamic programming problem is perturbation invariant if by changing everyone else's position, as long as the aggregate distribution is the same, I have the same decision. Okay. And this is how it's going to evolve for the law of motion for the aggregate shocks and for the idiosyncratic shocks. And then I can prove the first theorem. I'm slightly embarrassed to call this a theorem because it's so trivial. So I don't know, let's call it a proposition. The optimal solution of a perturbation invariant dynamic programming problem is in itself perturbation invariant. That is, if this is my optimal solution, this is also my optimal solution for every perturbation. And if this is my value function, this is also the value function for all perturbation. Okay? And the proof is kind of straightforward. You don't really need to do much. Okay, very good. Everyone with me about perturbation invariance? So now we are going to start doing something that is a real result, not a trivial result. Well, the other one is real as well, but like non-trivial. That's what I wanted to say. Okay, so this proposition is based on Backstaff et al. 2019, but we need to do a couple of things to extend it. So imagine that we have a function f that is continuous and is permutation invariant, okay, under the symmetric group. Then what we are going to find is that there exists a latent dimension L that is going to be less or equal to n. And I know some of you are going to get worried about the equality, but I will come back to that in a second. And continuous functions rho and phi such that the function can be represented as the following. A function rho that depends on x, and then on some moments phi of the rest of the distribution. And this is equal. Okay? So basically what I'm saying is I only need to keep track. If I'm looking for a function f, I only need to keep track of my own state and some information about the distribution. Now, of course, in general, we are going to be looking for L's that are sufficiently smaller than n. Because if L is equal to n, we don't really gain much. Okay? But the point is, we are going to be able to design the phis in such a way that that's going to really bias a lot, where L is going to be much, much lower than N. So N is 10,000, L is only going to be 10. Okay? And let me give you a very simple example of how this works, and then I go back to why this should remind you of Crusoe-Smith. So take a function from 2n, so this is basically a string of zeros and ones, into R. If F is permutation invariant, it means that the only thing that you care about is how many ones you have in the string. That the 1 shows up in position 3 or in position 16 is irrelevant, because you can always translate them. Rotate them. Okay? That means that this function f with these entries cannot have at most n plus 1 outputs. Then phi is just going to be equal to the identity function, and rho just maps the sum of ones into the string into the n plus 1 outputs. So I have gone from something very complicated into something much simpler. Yes?
What is X uppercase? I.
Oh,
Argument of the five.
each of the arguments, each of the entries of the vector X. I'm going over here.
The Fi are the entries of the
big vector X.
okay.
Okay. So think about this as means, okay, or moments. And that's going to be my very second point. That should remind you of Crusoe-Smith. Why? I come back to the other question in a second. So what do you do in Crusoe-Smith? In Crusoe-Smith, you don't have n agents, you have a continuum, but what you say is I have a function v that depends on my own capital and the distribution of capital of everyone else in the economy. And I'm going to substitute it by a value function that depends on my own capital and the average capital. And that's just a vector, it's just the mean. So phi is just going to be the mean. Okay? So this is just kind of a generalization of Crusoe-Smith, except that instead of doing it with a continuum, we are doing with n, and instead of being means, I'm going to allow any type of transformation of this information. I saw several questions, one at least over there. Yes.
So this proposition essentially shows like Crusoe-Smith works. So
yeah. Yeah. It basically says, yes, so the very nice thing, and I'm going to emphasize it later, actually, if you really, if you think about it, Crusoe-Smith is really a neural network. It's just a very particular neural network. Okay, which says a lot about, how smart Per and Tony are. It's just that bringing in all the toolboxes of neural networks really allows us to think about ways to generalize the approach and have a little bit of a stronger foundation. Want to add something? Yeah.
We don't need economic facts. Like,
yes.
Poor people near the bar, it don't matter too much.
Yeah.
They can do this.
Yeah. Exactly. So then, let me make like a 30 seconds detour that may help a little bit. One of the reasons machine learning and deep learning in particular has become very popular is because they require less domain knowledge. So by domain knowledge, what people think about is the knowledge that you bring about this problem as an expert. Okay, so Crusoe and Smith, Per Crusoe takes the class with Rao Ayagar in Minnesota, knows about the Ayagari model, really knows about the poor people not mattering much in the deterministic steady state. So he kind of infers what the right form for the approximation is. So we are not criticizing Crusoe-Smith because they actually get it right for the setup. What we are saying is the way they are able to develop their approach is based on their domain knowledge that cannot be generalized to other situations. And what we are going to try to do here and later on in the other set of slides is to tell you how by using neural networks and deep learning, you can generalize that approach without the need to have very specific domain knowledge.
There's a numerical determinant
yes.
statistics.
Exactly. No, but the point is the following. What is our opportunity cost? Say I wake up in the morning. What is the opportunity cost in my life? Seriously, anyone knows? It's pretty obvious. It's my time. Okay? Pen makes me enough money that, what do I need? A second iPhone for? No. So the real constraint in my life is time to write better papers and write a book and things like that. So anything that saves me time is much better than spending 1 month of my life handcrafting one particular solution. Why? Because I can always go to Amazon Web Services and ask for another GPU. So why do you want to spend 1 month of your life handcrafting something, while by being a little bit brute force, you are going to be able to get the solution right? Fine, it cost me $200 more on Amazon Web Services, so what? That's not the constraint. Okay? And in fact, the evidence, I get to you in a second, the evidence that we have was that, I don't know if you know much about the history of deep learning, but before 2012, for instance, for ImageNet, which was the main competition for image recognition, always the winner was a handcrafted image recognition program, and it was the introduction of deep neural networks by AlexNet and all the people at Toronto, at McGill, that basically say, hey, forget about handcrafting, let's do this brute force, we are going to defeat any handcrafting. So handcrafting is not something you really want to do. You just want to say, what the heck, over-parameterize this and go ahead. Yes.
Just this proposition, like the worst case,
yes,
is just that the latent space
yes,
of the exact same.
Exactly.
So I don't know, like I believe that there exists a latent representation, but also if the worst case is just of the same dimensionality, it might not, like it's not the best guarantee in the world.
No, I understand, but the point is that I'm not telling you there is a unique fee. Okay, so what we have in the paper is we discuss how cases that look like the worst case is binding, you can find some other row and some other fee where then it's not binding anymore. Okay, so this is not say there exists one row and one fee. There is actually a whole class of rows and fees, and you can select the one that reduces L enough. Now, can be there problems where there is no row and no fee that reduces it? Maybe. We have not encountered any of them. Okay.
There's a question online. Is it important that f of x, little x and big x, little x is unidimensional?
Oh, no, this is just for notation.
There's another question online, which is about sometime before. Is the transformation, this is regarding embedding, is the transformation into vectors supposed to be injected? And you said that banks should have different, the same vector, right?
No, it's the same vector, yes, because you want to represent the word bank always in the same way. And what you do then is you operate on the word bank differently depending on the company it keeps. So yes, I will say that in general, it's probably the best idea is to have an injective embedding, but I could imagine circumstances where you may not want to have injective embeddings. But injective is not necessary and it's not sufficient. It's probably convenient. Yes.
What are the downsides of using this? Are there any downsides? I mean,
you need to code it. I don't know. What are the downsides? If we want to be critical with ourselves.
Say that again.
Okay, sorry. What are the downsides? You know, where have we buried the bodies? I mean, you used to be in New Jersey, so you know where a lot of bodies are buried.
So I think that the main downside I found was implementation.
Okay.
It took a while to get the code. There are some things that we had to implement, like the early stopping fallback, but we said manifold fallback. Now that we get it, it's probably better for you. But generalizing to new models would be.
Yeah, I guess it's one of those things that my experience. I mean, I have developed a few algorithms that became relatively popular in the profession, and I think that the first time you do it, or the first 10 times, it requires some learning of the details, and later when there's a little bit of an accumulated knowledge, I would say that that's the main thing. Okay. And okay, so remember permutation. I told you that there are two aspects of the course of dimensionality. The first one is reducing the dimensions. The second one was the concentration of measure. Now, I don't want to spend a lot of time because this is a little bit of probability theory. Now, I want, however, to warn you about something. High dimensional geometry has an intuition and a set of intuitions that are very different from three-dimensional geometry. So be very careful about it, okay? A lot of you are going to think about geometry and probability, bringing intuitions from three dimensions. Those can be very misleading. For instance, the fact that the typical set is not at the mode of the distribution. So the concentration of measure is going to say, imagine that we are drawing from some distribution Z that comes from a norm. Okay, with some spectral values. And imagine that we have a function f, and the only thing I'm going to do is I'm going to bound the expected gradient. Then what I'm going to tell you is that the probability that f evaluated at the draw of the distribution is more than epsilon away from the expectation is bounded by this. And this bound depends on n in the denominator. In other words, I'm making this very small and n grows. This is the sense in which this looks a little bit like a law of large numbers. What is going to be the function f? The function f can be a value function, can be a policy function. But I'm making the statement not about the z's, I'm making the statement about the f's. That's the sense in which you can think about this as an endogenous object. Okay? The way Ledoux put this in 2001 is if you have a random variable that depends on ellipsis way on many independent variables, but not too much on any of them, then it's basically constant. Okay?
What's a C?
C is just a constant, no? And it's a constant that depends on the properties of the problem on the F.
It's kind of, I mean, I was wondering whether we can think of this intuitively, okay, there's like a big N, so there's like super many shocks sitting in all different directions, essentially they just wash out, so we kind of don't move a lot.
That's the way you want to think. So imagine, okay, so this is actually, no, that's a great question. So imagine that you have a model where you can have either high or low productivity. In the continuum, and the probabilities are 50-50. In the continuum, a law of large number holds, and we know that 50% of people will be high, 50% will be low. There is a paper by Harald Uhlig in economic theory that he actually proves that law of large numbers. This is saying we don't have a continuum, we have 1,000 agents, so you are not really going to get 500, but most of the times it's going to be 499, 501, or 402, and 498. Okay, but you are not going to get 600 and 400. Yeah. The probability that will happen is vanishing small. Okay, so that's it. So let me show you now how we apply this in concrete. Okay, and I'm going to show you the Lucas-Prescott model, which is a permutation invariant economy. So imagine that we have an industry consisting of n firms, where n is larger than 1, and each is producing the same good. And a firm produces output X with X units of capital. You see how silly this is? I mean, this is, and the reason we are doing it this silly is because in that way we are going to have a closed form solution. So I have 3 units of capital, I produce 3 units of good. And then the vector X, which is just the vector of all the capital in the economy, in the industry, is also the vector of production. And we are going to have an inverse demand function for some parameter larger or equal than 1, and this is our twist. I'll come back to that in a second, such that the price is given basically by this. So imagine that this parameter epsilon is equal to 1. Then this is basically saying the price is just a negative function of the sum of the production in all the economy. That's the original Lucas-Prescott model. And now let me make that epsilon later on larger than 1. This is some type of nonlinear effects for whatever the reason. And that will be my nonlinear economy. But why is this permutation invariance? invariant because over here, the only thing that matters is your x to the parameter. It doesn't matter in the way it enters into the sum. Okay, so if you have (0.3) and 0.2 as the distribution of capital in the industry, you are going to get the same price that if you have 0.2 and 0.3. The labels do not matter. The only thing that matters is the distribution itself. That's why this economy is permutation. Okay, and as before, we assume that the firm doesn't consider its own impact on the aggregate industry. We need to give it a twist to make this a linear quadratic problem. So the way that Lucas and Prescott did it was to assume that you can invest on increasing your production capability, but it comes at a cost that is quadratic. So the law of motion for your capital is just going to be your capital today minus your depreciation plus what you invest, and then we are going to have idiosyncratic shocks. Sometimes your capital grows or decreases for whatever the reason, an aggregate shock. Okay, and the firm is trying to maximize, is trying to pick you to maximize, and I'm sorry because you don't see that, let me move it, see if we can see over there. Okay. You are just trying to maximize, this is the price, this is what you produce, so this is your revenue, this is your investment cost, this is the discount factor, you are trying to maximize the present discounted value of your profits. Very good. So, this problem, as I was saying before, had that recursive form representation. I'm not going to go over it because it should be now very obvious, but the important point is that it's permutation invariant. Okay? And I can define a recursive permutation invariant competitive equilibrium. And the only interesting thing that I want you to get out of it is that we are going to have an Euler equation that has this form. Okay, so the firm is trying, this is my investment decision today, this is my cost, because remember, this is my marginal cost, it's quadratic, so the marginal one is linear, and this is the benefit that I get out of it, which is my extra revenue and my undepreciated capital tomorrow. Okay. So we want to find this solution that is accurate enough. And the problem is that even if the theorem says that if you know rho and phi, you can have the exact solution, the theorem is not telling you what that rho and that phi is. So you need to come up with an approximation to these functions. And that's exactly what neural networks are going to do. Okay, so up to this moment, neural networks really don't play any role. Everything that I have been exploiting so far is symmetry. Now neural networks come. And that's the whole point about how symmetry determines the neural network we are trying to build. And that's what we are going to do. We are going to define an architecture, and we are going to do two things. First, we are going to pick phi. Remember what enters into the sum. We are just going to pick moments, like in Crusoe-Smith. But we are going to let moments enter in fully nonlinear ways, like in my paper, it just came out in Econometric. I guess I need to update that. 2022 or 23, I don't remember. And we use either 1 to 4 moments. The other thing that we are going to do is approximate phi as a flexible ReLU. Why I like that? Because it's saying I'm agnostic. I don't know if moments matter or not. Just let me do ReLUs, and that's the end of it. And then that means that the approximation with moments and ReLU will have either 50,000 parameters coefficients or 67,000 coefficients. So I will need to minimize my loss function with respect to the 67,000 coefficients. And in all cases, rho is going to be a highly parameterized neural network with 4 layers. Okay, so this is the architecture. In the case we are using moments. So basically the little x goes over there. The big x's go over here. I take moments. I put this into the neural network, and that gives me u. And this is the architecture with ReLUs. I take these x's, I ReLU them, I take the small x, I get this thing, and I ReLU it again. Yeah.
Here's one drawback of the machine learning approach versus like the writer linearization.
Yeah.
Our approach, once you have the latent space, is very fast.
Yeah.
Finding the latent space requires computing.
Yes.
Generalized nomenclature, same with the DCAM.
Yeah.
If you look at the writer approach where you get the linearizer on the steady state,
Yeah.
observability matrix. Once you have this, you can grow it as cheaply with the
Yeah.
but then the performance is going to be worse.
Yeah. Yeah. That's a very good point. So this will be the algorithm. So basically, you fix the network architecture. So you decide if you want to do ReLUs or you want to have moments. And then basically what you are going to do is you are going to define the Euler residuals. So you see, Simon, we are not using value function.
Yeah,
So you should be happy.
Not nervous anymore.
Not nervous anymore. You know, we can relax and go to the pub. And basically what we are going to do is simulate the model. Let me forget about some of the details. And we just pick the parameters of the neural network to minimize the Euler equation errors, as we have learned over the last couple of days. We use Adam, 67,000 parameters for Adam is not a big deal. And we are going to parameterize the model. Again, in the interest of time, because I still want to tell you quite a few more things, let me skip it. The only thing is I'm going to have the case where the demand function is linear and the case where the demand function is not linear. Why the case where the demand function is linear? Because then I know that I have a linear, an LQ solution, that actually that problem, this economy, if you have taken science class, you know it's the linear quadratic regulator problem. So you know how to solve this very efficiently and exactly, well, up to machine precision. And what I can show you is the difference, I think I'm getting this right, between the exact solution from the linear quadratic regulator and the solution from the neural network. And you see that this is 10 to the power of minus 12. Okay, so you absolutely nail it down.
Last question.
Yes.
So like, did you store the network in semi-precision?
Why? Because you want to go.
Negative 12 if you have
No,
semi-precision?
no, it's 10 to the minus 7.
10 to the.
Okay, sorry. My bad.
Okay. No. Oh, and I forgot to say this is for 128 firms in the economy. And then, yes.
How do you find L? Maybe I'm.
Okay. L is part of the architecture decision. So remember, I don't know rho and I don't know phi. Okay? And L is really this thing over here. So what I'm going to do is I'm going to approximate this with ReLUs or with moments, but let me just say ReLUs to save on time. I'm going to approximate this with ReLUs and then this with ReLUs. That's how I approximate it. Okay? And then, as I was saying before, you pick in the design of the architecture enough flexibility that you can do that. Yes.
The solution to the LQ dynamic programming problem, H0 and H1 are what?
They are just things, they are in Sarian textbook, they are just two coefficients that are very easy to find.
Okay, so like we can get actual numbers for them.
Yes.
They have specific values to say.
Yes.
How the same function for each player, for each firm.
Yes.
How do you get 60,000 parameters? I would then think like you would have to mean the variance, skewness, and those as your DOMs, 4 parameters.
Okay.
Fine.
So this is the beautiful thing that if you stick around until we talk about on Saturday, no? About the double descent phenomenon. So yes, in principle,
4 is fine.
4 will be, well, not quite. For the linear case, yes. For the nonlinear case, not necessarily. You may need more. But the point is, don't worry about over-parameterizing this thing. You just throw into a ReLU, have the 67,000 parameters, the minimizer will pick it, and it will be the right solution. So in fact, we have an example in the paper where the solution is in fact linear, and you could get it right with only 2 points. And the neural network, even if it's kind of minimizing over 70,000 dimensions, gets the linear solution right. Okay, so that's not a problem for the neural networks. That the idea of somehow I'm over parameterizing and I'm not overfitting, etc., like that, that's not a problem over here. Because basically what the neural network is going to do is search over all these different combinations of the 70,000 parameters. That gives you something that is linear, and that's it.
It's slightly related, like I'm wondering why do you use this result about the representation of the function and don't just symmetrize the input vector? I mean, given this is all sort of TensorFlow, why you could use something like the symmetric tensor, I guess, or something, right? To just symmetrize the input as a vector already. And then you would have like a given reduction, I guess you could calculate what that L would be. And then you would already work on a lower dimensional space with this.
Yeah, but the problem over there, okay, so that's in some sense what Packes and Ericsson do. So what they do in their model is they basically say, remember when I was doing before H, L, H? Basically what they do is they say, my value function is going to depend on my H, and then over here I'm going to have a counter for how many H's I have. So this is what I'm going to compute. I'm going to compute the value function of H and 3. Okay. The problem of this approach, to me, is that you may have like a very highly dimensional set of variables over here. So you will need to have like indexes of many things over here. Like imagine that it's just not productivity, it's productivity and the type of models they have and their demand shocks, etc. And then how do you approximate a highly dimensional value function? Well, what we are saying is, no, don't worry about that, because this is going to depend on the L directly, and that's what I'm going to try to approximate. Well, in this case, it's going to be the decision rule, not the value function, but the point is the same. Okay, so that's why I'm trying to do the dimensionality reduction in the policy function already and not in the input. Because the dimensionality reduction in the value function is, yes, it's going from a problem that is absolutely intractable to something that is way more tractable, but it's still going to encounter one particular form of the course of dimensionality, which is the dimension of the vector where I have reduced the industry dynamic.
We did try it that way.
Yeah, I know. That's why I think that there is a very simple extension of this paper, which is just to redo Ericsson and Packes with this approach and show that this scales Ericsson Packes much more.
But sort of you were using indices or something, not sort of a fully symmetrized vector like tensor.
Yeah, okay. Anyway, and then we also do the nonlinear version. And in the nonlinear version, now you look at the Euler equation errors, and they are the order of 10 to the power of -6. And again, we have 128 firms. And to me, that's pretty impressive. Solving an industry model with 128 firms, I'm doing it with a very, very high precision. Yes.
So first, so you're approximating both like these phi function and like the firm value function?
Yes. Well, I'm approximating the policy function, and when I have the policy function, I can compute the value function.
Yes, sure. And second, would there be any complication in such a setup, like the payoff would depend like in a less obvious way? I mean, right now you have a setup where you know all the states, you know immediately all the payoff. What if there will be, I don't know, the firms can choose capital utilization, say some setup where it's like not where you cannot directly.
No, I don't think
like any complication.
No, I don't think so. I don't think so, because the only thing that will happen is that this function U will be two-dimensional. So the first dimension is the investment, the second one is the capital utilization. And algebraically, maybe more costly, and you may need to parameterize the neural network a little bit more, but at the end of the day, it's the same. Because the only point I'm doing over here is I'm saying I'm finding the decision rule of the firm. The decision rule of the firm can be defined as many different variables as I want. Okay.
Yes.
Again, I'm only doing this with one choice, so I can fit everything in one slide. Couple of cute little points, and then I go to the second set of slides, is you can actually show, and this is quite amazing, that this problem is big O1 in the Landau notation basically says it doesn't suffer from the course of dimensionality. It's actually constant. There are very few cases in economics where you can get stuff that is 0.1. Now, of course, O1 doesn't tell you about the level. It can be high, but it's basically saying the computational complexity of solving it, as I'm showing you over here, with 10 firms or with 10,000 firms, is roughly the same. Now, you may run out of memory, okay, because you are computing all these state vectors, all these vectors, etc. But that's a problem of memory. It's not a problem of the GPU, the CPU.
Yeah, I was asking.
Yes.
So that increase in the number of states does not force you to increase.
Yeah. Okay. Anyway, there is a lot of stuff over there. So let me just point out examples that I think could be interesting. Again, I'm jumping a lot of results, so take a look at the paper. I think some of the results are cute. But now I could imagine things like having decreasing returns to scale. That will be trivial. I only had constant returns to scale to have an LQ regulator problem. We can have multiple productivity ties, complex idiosyncratic states, non-atomic agents, many different network architectures, etc. And also type of models where one could think now about computing with this technology, which I really think is very nice. These models with rich ex-ante heterogeneity and aggregate shocks, models with thermodynamics, open economy models with many locations, closed economy business cycle models with the sectors, which is what I'm doing with Christian and Hikaru right now, network models, search and matching, etc. So there's really a lot of things that can be done once you realize that in our standard model, symmetry is the default. Yes.
I think at the beginning, the kind of a simplification was to switch off the strategic component.
Yes.
This only changes the Euler equation, or it has more limitations?
It only changes the Euler equation. The only thing will be when I think about the law of motion for the aggregate states, I will need to take account that that law of motion comes from the Nash equilibrium. That's what I will really need to consider.
And in case you have sequential games, anything before you include as a state variable.
Well, but I will probably do Abropir's Stacketi with sequential games. I will probably do it in terms of continuation utility, not in terms of past strategies. Because the problem when you're computing sequential games, you know the paper by Abropir's Stacketi, Econometrica, like 1995, 1996. So basically, the problem is if you have a sequential game, the space grows as the game unravels. So it's not stationary, the dimension is not stationary. So what Abro, Pearson, and Stacketi say is, no, this is silly. What you want to do is you want to encode all the information about the sequential equilibrium in a continuation utility. So you can think about this as value function to the square, okay? Because you have both your value function today and you have all your continuation utility as a state variable. It's the continuation utility of the sequential equilibrium. And then you can characterize the whole solution. My suspicion, the problem why Abropir's Stacketi did not become the next big thing in economics was because computing that continuation value was actually extremely complicated. I had a paper that I tried very hard with Alex Sivinsky for like 2 years and we could never get it to work. My suspicion is that one could revisit Abropir's Stacketi with this technology and actually solve it much more efficiently. Okay? There was a version computed using computational geometry, also in Econometrica, by Ken Judd and two of, what is the name of your team? The name of your team.
Steve had a paper.
Yeah, that's the one. It's Ken Judd with the team at Carnegie now.
I did one with unsupervised partial
Yes.
on that too.
Yeah, I should. Yeah.
Another explanation why this works, could that be that the representation of the distribution,
yes,
that the pulse function is robust to perturbations of that distribution?
No, that's the wrong way to think about it, sorry. The point over here is I'm high, and the rest of the economy is low, high, low, high. My decision rule is the same, that if I'm high and the rest of the economy is high, high, low.
But
that's the point.
But that's kind of if like you're still making some sort of Latent representation of the distribution.
Yes, that's the point I'm trying to say. You are the only thing that you care about is that in this world there are 2 lows and 2 highs. Who has the low and who has the high is irrelevant.
Yeah, but I totally get get that. It's the representation that when you use the neural network to map it down to a low dimensional space.
Oh, no. We are not using this theorem. Has not used any neural network. Okay.
I know that, but that's what's my point, right? It's very generous guarantee.
Yes.
It guarantees that exists some latent. You don't know if you get that.
Yes.
And my point is the phi rho.
Yeah.
Right. The point is your policy function might just be robust to permutation to the underlying distribution, right? So it's more like a robust statistics argument that really carries the result more than the symmetry argument.
I don't see it like that, but I'm not.
Yeah, okay. We can go out.
Okay, so these are, I hope that, people pick up some of this idea, try to apply this to different circumstances and see.
One more question about this result on the concentration of the nature. So what's the implication of this concentration of the nature in terms of how we should do sampling?
Yeah, so the main point is when you are looking for that expectation, in that expectation, instead of worrying too much about computing that expectation very, very accurately, just sample once from the whole distribution of idiosyncratic shocks. And when you evaluate that integral, even with one draw from the distribution will be good enough.
But, so for example, in the example of Kursor-Smith,
yeah.
I think the reason that I think in DPM we try to do multiple simulation is that we sort of need to sample the initial distribution
yes.
of all the agents.
Yes.
So which means that we need to have multiple.
I know what you mean. Yes, yes. Okay, so the difference over here is that we are implicitly. Okay, so how do I say this in a relatively simple way? We actually compute transitional dynamics. We found that for this problem, the number of samples we needed to get the transitional dynamics right was actually not very high. But I can see other problems where you may need to measure. Okay. The point of the concentration of measure is that you probably don't need to sample as much as you think you need.
Problem.
That's not its standard.
Like conditional on the initial distribution, then you don't need to sample.
No, but the initial distribution, yes, that's always okay.
Better than stochastic gradient that you just sample once, period, not even once per. You just hash it.
Okay, very good. So let me go to the second set of slides. And there's a lot of material over there that I'm going to skip. And I'm going to jump directly into models with heterogeneous agents. If I can see where, okay. I wanted to click that. Can anyone kind of help me? I'm just not used to these Windows mouses. Okay, thank you. You should be slightly suspicious that I'm claiming how to compute these models. And then I can. There's a very famous person in the profession, I'm not going to name names, that has proven very important theorems in computation, and I seriously doubt he knows how to send an email. Anyway, theory and applications are two different elements. Anyway, so what I want to do during the last half an hour is to tell you a little bit more about how to solve models with heterogeneous agents in a very general setup. And the way I think about this is the following. To compute and take to the data models with heterogeneous agents, you need two things. You need one, to have the distribution of agents GT. And the second is you need to have an operator H that characterizes how this distribution of agents evolves. If you are in discrete time, the operator H maps the distribution G given some aggregate states ST into GT plus 1. If you are doing this in continuous time, what you have is the partial derivative of G with respect to time. By the way, why you may want to do a heterogeneous agent models in continuous time? Because you are going to take advantage of the Ito's lemma. And the Ito's lemma is going to tell you that the complicated expectations that you have in the Hamilton-Jacobi-Bellman equation are going to disappear. So as long as you can evaluate quadratic forms sufficiently fast, it will simplify your life. That's why, you know, a lot of people these days are using heterogeneous agent models in continuous time. So solving a model with heterogeneous agents at its core is about two things. And this has nothing to do with neural networks. This is about every single model with heterogeneous agents, from industrial organization to open economy macro to finance to labor economics. One, how do you track GT? And second, how do you find the operator H that maps the distribution today into the distribution tomorrow? Well, if you are in a model where you have n discrete types, so high risk aversion, low risk aversion, or high risk aversion, middle risk aversion, low risk aversion, the only thing you need to do is keep track of the n-1 weights that we were saying before. So remember what I was saying before, that your value function will depend on your productivity and the counter of how many firms have high productivity. So that will be basically the distribution. If you have high and low, you only need, which will be n equal to 2, you only need to keep track of one object, which is the counter. I can write this either 2, or if they are like 4 firms, 2/4 as a share. If you are dealing with a continuous types, then this is where the problems start. Because how do you represent that into the computer? So we can go back to the original idea of Kruskal and Smith and store the distribution as a set of moments. That may be good enough, or maybe not good enough. We maybe want to do it in terms of key quantiles. Okay, so you have a lot of quantiles and approximate the distribution as well as you want, or you can have weights in a mixture of normals and express your distribution as a mixture of normals. But whatever choice you make, you are going to stack either the weights or the features of the distribution in a vector view. And now this is a finite dimensional vector. Okay? And what we are going to assume is that mu of t follows an operator lowercase h that operates on mu of t instead of the capital case H that operates on GT. So what have we done? We have said, look, we have this operator capital H that if it depends on a discrete number of types, is trivially reduced to lowercase h. But if it depends on a continuum, I need to summarize G into some features. And then what I'm going to do is I'm going to parameterize this operator H given some coefficients. And I'm going to try to find those coefficients in a way that the solution of the model approximates the true solution, or the exact solution, let me say it in that way, as close as possible. So there are two problems here. One, if the distribution is continuous, how do I extract features? And second problem, how do I parameterize the function lowercase h? So what do Kruskal and Smith say? They say, well, I'm going to summarize the distribution over assets in the economy by the mean. In fact, it's going to be the log of the mean of capital, and I'm going to parameterize the law of motion as a linear regression. That is going to be state dependent because this is going to depend on the aggregate state variable being high or low. So what basically you're saying is the log of capital tomorrow is a linear function of the log of capital today, where this is a state dependent. Okay, so that's how Purcell and Smith tackle the two problems. How do I represent the function? The mean. How do I represent the law of motion as a log linear function? Does it work? Yes, it does. But coming back to the discussion before, it works because Per and Tony are very smart. They understand the problem very well. They sit in front of the computer for 2 years and they say, is this? But this is not a constructive approach to extract features from a distribution and to build the operator. So what can you do? In principle, one could use deep learning to extract features from a distribution in an efficient way. Okay? I have been thinking about working on this problem for a while. I haven't had the time. But that's a good research project because there is some research on distributional deep learning. Okay? So in principle, I can throw some type of neural network to an arbitrary distribution, and that will extract the features that I need to approximate the operator as well as I can. Since I haven't figured it out how to do that, I'm going to follow the approach of just taking some key quantiles. Okay? And I'm going to take advantage that that neural networks break the course of dimensionality to have as many of these quantiles as I want. My suspicion is that, at the end of the day, you have like 99 quantiles that will probably, nail the heck out of that. And then what I'm going to do is I'm going to approximate the operator h, lowercase h, as a neural network. You see? And why is this a very efficient way to do things? Because it's just a function. This is a finite dimensional space. This is finite dimensional, and this will give me the mu t tomorrow. I'm just trying to find a function that maps finite dimensional spaces into finite dimensional spaces. And that's just the standard thing we have learned neural networks can do. And the way I'm going to propose to do it is just by simulation. So I have a model. It has a lot of stuff, but I'm not going to bore you up with it. So let me go directly and tell you exactly what we are going to do. So this is a model with heterogeneous agents and financial frictions and yada, 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 yada. The type of things that make editors happy and referees happy. Okay. So I'm going to have this distribution of households. And I'm going to summarize that distribution of households with some moments. Turns out to be the case that we learned, to our big surprise, that even the mean, as Purcell and Smith suggested, is enough. Okay? And then what I'm going to do is I'm going to parameterize in the interest of time. Instead of using the slides, do you really mind if I just go like old style? Oh, sorry, but I just want to stop sharing the screen.
You think that's
Yeah, I know. But anyway.
now you're only good.
Okay, fine, very good. Yeah, but I didn't want to have like some. Okay, fine. So what I'm going to say is the following. So I'm going to have a function h, which is going to depend on the average of actually the asset position of the households. Okay? And it's also going to depend on the aggregate shock. This is not exactly the model in the paper, but this will be a little bit easier to see. Okay?
Age of distribution of households.
Okay. This is the mean of the asset holding by the households. Okay? So this is a distribution of assets, and I'm just parameterizing with the mean. But I could have many more moments. I can come back to that in just 1 second. And I'm going to say, and remember, this is what is going to map into the mean tomorrow. Okay, the mean of assets today is the mean of assets tomorrow. Sorry. Given the mean of assets today and the aggregate shock, I'm going to have the mean of assets tomorrow. What I'm going to say is I'm going to parameterize this as a neural network, where this is going to be my activation function that depends on ATCT, and that depends, what is the notation I want to have, because this is the weight and this is what enters inside. Okay, so this is a one-layer neural network. We could do it more sophisticated with more layers. But I basically say a constant, the weight of each of the activation function. So let's say this goes from 1 to 20. Okay, this is the activation function. And what I have inside the activation function is just the linear translation of A and ZT, which is just a coefficient AT, another coefficient ZT. And this is exactly my example before about the ball, remember? I'm basically taking the AT and the ZT, and I'm translating them, and then I'm rotating them, and then I'm summing them again, and I'm doing that 20 times. So how does this look like? A lot like the original Kurzweil-Smith? Because what Kurzweil-Smith do is they think about this activation function just as the log. And that's it. What I'm telling you is instead of having the log, I'm going to have a marginal activation function. And instead of doing it once, I'm going to do it 20 times or as many times as you need to get this to approximate as carefully as you need. Everyone with me? Yes.
Just a little bit of curiosity, like since you said you also considered the other case, for example, in the context of the model you studied in this paper, like how much more costly would it be, like agnostic and say, okay, we're going like one shot?
Now, not that much. I mean, the thing is, when we started doing this many years ago, more years ago than I can care to remember, computing these neural networks was still complicated and there was not that many libraries. So we didn't really do a lot of exploration. Now it will be way easier. And in some senses, what we saw this morning. Okay, but the very nice thing is remember that AT, now I'm going to change AT by a vector. I'm going to use that awful notation that physicists like for vectors. Okay, so now this is just not the mean, this is a vector of the distribution. This will be a vector, and this will just be a vector transpose. And the good thing is that this is not going to really matter much because neural networks break the course of dimensionality. So how I'm going to solve this? Well, exactly the same way that Simon showed us this morning. I'm going to have some initial values for these coefficients. I'm going to simulate the economy. I'm going to define some loss function, some criterion, which will depend on your particular problem. But for instance, something that we use in our model is, oh my God, what did we use? the evolution of that, whether or not aggregate debt was what's supposed to be. But anyway, you are going to define like some Euler equation error or some other criterion, and you are going to retrain the thetas. You simulate again, you retrain the thetas, you simulate again, you retrain the thetas until convergence. And that's the sense in which I was telling you before that Crucell-Smith is really a neural network, because that's what they do. They put over here a log, they forget about this sum. Okay, so it's a neural network with logs as activation function and one neuron. But that's still a neural network. They get some values, they run the simulation, they retrain the network. The retrain in this particular case is just by OLS, but we know that OLS is just a particular way of gradient descent. And they get a solution and they keep doing it until convergence. And for their very particular case, that very particular network architecture, if I can put it in that way, actually works. What I'm doing over here is I'm giving you a constructive way to do it in a much more general way, which is pick any type of moments or quantiles that you want from your model, write it in terms of an activation function, ReLU will be good enough, or soft plus, and just do the standard ADA optimization. Yes?
What's the loss function?
So the loss function, I don't want to get into more details because it will depend on the model. Okay, but think about some type of Euler equation error or value function error if Simon is not a value. But I'm trying to do all this at a very abstract level for any type of heterogeneous eigenmodel. But the point is, at the end of the day, I want to approximate what you want to say is in my heterogeneous eigenmodel, what is my operator H? Okay, let me parameterize that operator H as a neural network. That's the key. I saw some more hands. Anyway, so let me stop here because I think it's 5:19. But what I have tried to show you in this presentation is how to think, hopefully in a sufficiently general way, about models with heterogeneous agents, be either finite or infinite. And what I did in the first half of the presentation was to argue, if in addition to it, full thing is finite, you can also exploit some forms of symmetry. Okay, so it's 5:20 sharp.